In this video, I am going to show you Isaac Newton's theory of optics from a modern perspective. Starting from the basics, I will be explaining what it is and how it works. Sir William Bragg said, "Light brings us news of the universe." Astronomers reveal many of the universe's secrets by exploiting the physics of light. Isaac Newton was one of the first to try to understand its nature. Passing white light through a glass prism, he found that it split into rainbow hues and showed that the colors were embedded in the white light rather than imprinted by the prism. Today we know that visible light is one segment of a spectrum of electromagnetic waves, stretching from radio waves to gamma rays. Shine a beam of white light through a prism and the emerging ray spreads out into a rainbow of colors. Rainbows in the sky appear in the same way. Sunlight is split by water droplets into the familiar spectrum of hues: red, orange, yellow, green, blue, indigo and violet. Experimenting with light beams and prisms in his rooms in the 1660s, Isaac Newton demonstrated that light's many colors could be mixed to form white light. Colors were the base units rather than being made by later mixing or by the prism glass itself, as had been thought. Newton separated beams of red and blue light and showed that these single colors were not split further if they were passed through more prisms. Light waves. Experimenting further, he concluded that light behaves in many ways like water waves. Light bends around obstacles in a similar way to sea waves around a harbor wall. Light beams can also be added together to reinforce or cancel out their brightness, as overlapping water waves do. In the same way that water waves are large-scale motions of invisible water molecules, Newton believed that light waves were ultimately ripples of minuscule light particles, or corpuscles, which were even smaller than atoms. What Newton did not know. Something that was not discovered until centuries later is that light waves are electromagnetic waves, waves of coupled electric and magnetic fields, and not the reverberation of solid particles. When the electromagnetic wave behavior of light was discovered, Newton's corpuscle idea was put on ice. It was resurrected, however, in a new form when Albert Einstein showed that light may also behave sometimes like a stream of particles that can carry energy but have no mass. Across the spectrum, the different colors of light reflect the different wavelengths of these electromagnetic waves. Wavelength is the measured distance between consecutive crests of a wave. As it passes through a prism, the white light separates into many hues because each hue is deflected to a different degree by the glass. The prism bends the light waves by an angle that depends on the wavelength of light, where red light is bent least and blue most, to produce the rainbow color sequence. The spectrum of visible light appears in order of wavelength, from red with the longest through green to blue with the shortest. What lies at either end of the rainbow? Visible light is just one part of the electromagnetic spectrum. It is important to us because our eyes have developed to use this sensitive part of the sequence. As the wavelengths of visible light are on roughly the same scale as atoms and molecules, hundreds of billionths of a meter, the interactions between light and atoms in a material are large. Our eyes have evolved to use visible light because it is very sensitive to atomic structure. Newton was fascinated by how the eye worked. He even stuck a darning needle around the back of his eye to see how pressure affected his perception of color. Beyond red light comes infrared, with wavelengths of millionths of a meter. Infrared rays carry the sun's warmth and are also collected by night vision goggles to see the heat from bodies. Longer still is microwaves, with millimeter to centimeter wavelengths, and radio waves, with wavelengths of meters and longer. Microwave ovens use microwave electromagnetic rays to spin the water molecules within food, heating them. At the other end of the spectrum, beyond blue, comes ultraviolet light. This is emitted by the sun and can damage our skin, although much of it is stopped by the Earth's ozone layer. At even shorter wavelengths are X-rays, used in hospitals because they travel through human tissue, and at the smallest wavelengths are gamma rays. Astronomers look at the universe at all these wavelengths. Photons. But light doesn't always behave like a wave. Newton was partly right. Light rays do carry energy that is delivered in tiny packets, called photons, which have no mass and travel at the speed of light. This was realized by Albert Einstein, who saw that blue and ultraviolet light shone on a metal setting up an electric current, the photoelectric effect. The currents are generated when metals are illuminated by blue or ultraviolet light, but not red light. Even a bright beam of red light fails to trigger a current. Charge flows only when the light's frequency exceeds some threshold, which varies for different metals. The threshold indicates that a certain amount of energy needs to be built up before the charges can be dislodged. In 1905, Einstein came up with a radical explanation. It was this work, rather than relativity, that won him the Nobel Prize in 1921. Rather than bathing the metal with continuous light waves, he suggested that individual photon bullets hit electrons in the metal into motion to produce the photoelectric effect. Because each photon carries a certain energy, scaling with its frequency, the bumped electron's energy also scales with the light's frequency. A photon of red light, with a low frequency, cannot carry enough energy to dislodge an electron, but a blue photon, light with a higher frequency, has more energy and can set it rolling. An ultraviolet photon has more energy still, so it can slam into an electron and donate even more speed. Turning up the brightness of light changes nothing. It doesn't matter that you have more red photons if each is incapable of shifting the electrons. It's like firing ping-pong balls at a weighty sports utility vehicle. Einstein's idea of light quanta was unpopular at first, but the climate altered when experiments showed his wacky theory to be true. It confirmed that the energies of the liberated electrons scaled proportionally with the frequency of light. Wave-particle duality. Einstein's proposal raised the uncomfortable idea that light was both a wave and a particle, called wave-particle duality. Physicists are still struggling with this tension. Today, we even understand that light seems to know whether to behave as one or the other under different circumstances. If you set up an experiment to measure its wave properties, such as passing it through a prism, it behaves as a wave. If instead, you try to measure its particle properties, it is similarly obliging. It is truly both. Matter waves. In 1924, Louis-Victor de Broglie suggested the converse idea that particles of matter could also behave as waves. He proposed that all bodies have an associated wavelength, implying that particle-wave duality was universal. 3 years later, the matter-wave idea was confirmed when electrons were seen to diffract and interfere just like light. Physicists have now also seen larger particles behaving like waves, such as neutrons, protons, and recently even molecules, including microscopic carbon footballs or buckyballs. Bigger objects, like ball bearings and badgers, have minuscule wavelengths, too small to see, so we cannot spot them behaving like waves. A tennis ball flying across a court has a wavelength of 10-34 meters, much smaller than a proton's width.